All right, welcome to Unit 14, Acids and Bases. This unit serves as an introduction to acids and bases, which will actually be the topic of our next three units, making up the acid and base section of AP Chem. It's a very significant portion of the AP exam. Maybe 20-25% of the questions will come from these. And these build off a lot of the ideas we learned about in our last unit, Equilibrium, in Unit 13. So a lot of what we're doing is a little bit new, but also basically like the math we do in Unit 13. So we're going to go ahead and get started with it. I'm going to try to keep this as short as possible. Some of these questions take a good amount of time to solve, though. We're going to set up some ice tables and stuff like that, so it might take some time. Okay. So we're going to start with a couple of definitions of acids and bases. Acids were first classified as a sour substance, while bases were first classified as a bitter and slippery substances. These might have been like definitions you got in biology for like what an acid and base is before we learned more about what these chemical compounds are. And we're going to go through a couple of definitions, but this is just kind of the most general. If you were in your house tasting the various things in your pantry or in like your cleaning supplies, you might notice that things are acidic, taste kind of sour, like lemon juice, like like most juices and stuff, unless you had a bunch of sugar. Things like that are a little bit sour, and then bases would be usually things like soaps and detergents and stuff like that. They have a slippery feel and they're bitter. The first chemistry definition was through Arrhenius, called the Arrhenius concept, and this is sometimes how we'll think about an acid and base as well. He was the first person to recognize the actual chemical nature of acids and bases. Acids produce H plus, hydrogen plus ions in solution, and bases produces OH minus ions in solutions. Now, this is a pretty good concept when you're talking about aqueous solutions of things that dissolve in water, but this doesn't apply to all sorts of acids and bases. But this is a good general idea. Acids, when you put them in water, make hydrogen plus ions. That's what actually makes it acidic and what actually makes its pH go low. And then bases are very similar. They produce OH ions. Okay. A couple more definitions, but we'll start with just looking at some of the formulas here. So an Arrhenius acid, we're going to give it the general form HA. HA usually just means acid, and more specifically a weak acid. Is going to split into an H plus, and the A minus is the anion of whatever I was left with for my HA. And an Arrhenius base would be something made of a cation and OH minus. And then they split apart into those, the cation by itself and OH minus. So an acid is just anything that makes H plus ions in solution. A base makes OH minus ions in solution. A lot of the time, that's a good definition for us. That's how we'll think about acids and bases. Okay. The Bronsted-Lowry definition is a little bit more accurate. Okay. And this is most likely what we're going to use most of the time. But an acid is a proton donor. Okay. So an acid is anything that donates a proton. Now, H plus is just another word for proton. H plus is a hydrogen that lost one electron. A hydrogen, the normal hydrogen, is made of one proton and one electron. So if it loses that electron, all that's left is one proton. It doesn't have any neutrons on average. A base is a proton acceptor. So base is just anything that's going to gain an H plus in a reaction. Acids donate H pluses, bases accept them. Another sort of definition. By the way, none of these names are important to know. I'm not going to ask you, like, is this a Bronsted-Lowry acid base or anything? These are just kind of ideas of what acids and bases are to introduce them. Okay. First concept we're going to talk about that's important is the conjugate acid-base pair. It's two substances that are related to each other by the donating and accepting of a single proton. Okay? So these are kind of like, they're going to look very similar to each other, an acid and its conjugate base, or a base and its conjugate acid. Okay, so here is an example. This reaction at the top is also mirrored below with the model diagram below, but I start with HA, which is an acid. And I'm going to add it to a base. You see H2O is labeled as a base. If H2O as a base doesn't make sense, we'll talk about that in just a few minutes. Okay, but this HA, when it reacts, it's an acid, so it's going to donate its proton. Okay. So if it donates its proton, that means it's going to lose an H and it's going to lose a plus. And I'm going to see this acid over here, what it turned into when it lost its H and it lost a plus. It'll be left with just an A, and it now has a minus charge. It has the minus charge because it lost a plus, so it's like minus, right? HA is an acid. A minus is its conjugate base. And I would say this forms one acid conjugate base pair. You'll notice the two are only off by a single proton, an H plus ion. Now, if I look at H2O, H2O is acting as a base. If something is acting as a base, it is a proton acceptor, meaning it's going to add an H and add a plus. Okay, so when H2O reacts, it's going to go into H3O plus. It added one additional H and it added a plus. Okay, so that is a base and it's conjugate acid. Conjugate base is everything that remains of an acid after you lose the proton. Conjugate acid is formed when a proton is transferred to the base. Anytime we look at an acid and base reacting to each other, we can find the conjugate acid-base pair. So it's basically just things that look really similar. H2O and H3O are almost identical. They're off by a single H+. Okay. We can also look at a reaction and identify what is an acid and what is a base based on what it turns into. So kind of like I was talking about. HA turns into A minus. It lost an H plus and is therefore an acid. H2O gained an H and gained a plus, right? So it accepted an H plus and is therefore a base. We can write an equilibrium expression, just like we did in the last unit, for an acid in water. Okay? So here, take a second to write this down. Hopefully it looks really familiar. We're writing this exactly based off of this reaction on the previous slide. This reaction, we have HA and H2O on the left, H3O plus and A minus on the right. We're going to write our products over reactants, H3O plus and A minus, over HA. That's products over reactants. Now you might be wondering where that last reactant went. We had H2O as one of our reactants in the reaction, but it is a liquid. Liquids and solids are not included in the equilibrium expression for anything. Just like last unit, that'll apply here. Now you also might be wondering why there's two different equal signs here. We have H3O plus and H plus are the differences between these two. Those two are like identical ways to say the same idea. H plus and H3O plus. This is just H plus with a water molecule attached to it. So it just has an extra H2O. In real life, we would see H bonded more like this arrangement, H3O plus ions bonded together, giving things their acidity. But a lot of times, to simplify our calculations and as like a little shortcut, we just write H plus instead. Just know anywhere you see H plus, it's the same thing as H3O plus. You can write either, both are correct. They're both used to represent the hydrated proton. Ka is our acid dissociation constant. It's giving you a ratio of what percentage of your acid turns into products. Obviously, what percentage of my HA that I started with turns into H3O plus and A minus. Something with a high acid dissociation constant would turn into a lot of H plus or H3O plus. And something with a low Ka only makes a little bit of H3O plus. All right, so let's talk more about strengths of acids and bases. So starting with acids, the strength of an acid is determined by the equilibrium position of its dissociated reaction. Basically, dissociating means splitting apart into its two parts, its H plus and its A minus. So the stronger an acid is, the higher percentage of the acid molecule split into those two things. For a strong acid, now this isn't just saying generally like it's strong, like it's going to dissolve a lot. We use the word strong acid as kind of like a vocabulary term to talk about a specific type of acid. It's not talking about its concentration or anything like that, or how many moles of acid you have, or its molarity, right? It's just, by definition, a different type of acid than what we call a weak acid. There's going to be different math involved with both the different types. Okay? The ionization equilibrium lies far to the right, meaning with a strong acid, the entire thing dissociates. It makes a lot of products. All of HA, all of our acid, is dissociated at equilibrium. Because of this, they have very large Ka values, and they yield very weak conjugate bases. So here are a couple examples of some strong acids: sulfuric acid, H2SO4, hydrochloric acid, nitric acid, and perchloric acid. A couple other examples would be like hydrobromic acid, HBr, which I think I included for you on your worksheet. A weak acid, by comparison, is completely different. It's going to be a proton donator, but it doesn't donate super well. Not 100% of the acids donate their protons. It's going to be actually a really small percentage that actually do. By definition, with a strong acid, which we'll get to a little bit, 100% of the acid molecules donate their protons. But with the weak acids, it's not true. The equilibrium lies to the left, actually. Only a small percentage of a weak acid's molecules can donate their H pluses. The weaker the acid is, the stronger its conjugate base. So we'll kind of talk about how that works. Most of the original acid is still present in HA at equilibrium. Because of that, it has a very small Ka value. And here are a couple of common weak acids you should know. Acetic acid, HC2H3O2. It's called acetic because it's acetate plus an extra H, so acetic acid. Same thing with phosphoric acid. It's phosphate with 3 H's. Nitrous acids from nitrites. And then hydrofluoric acid is HF. Those are 4 of the most common ones I'll use on our tests and worksheets and stuff. Couple more definitions here. Types of acids. All acids will have between 1 and 3 protons. It says these are acidic dissociable protons. Basically, how many protons does something have to lose? Almost all the time we'll be dealing with monoprotic acids, which just have 1 proton, just 1 H. Something like hydrofluoric acid here, HF. A diproduct has 2, like H2SO4. That means it can actually act as an acid twice. It can lose its first H, and then its leftover would be HSO4 minus, can lose another H as well. And a triproduct just has 3 acidic protons that can all be lost in series. We'll talk about those very little, but mainly monoprotic acids what we care about. Okay, I said I'd mention water a little bit. It was weird that it was a base, because you usually think of water as being neutral, and it is. But water is amphoteric, meaning it can act as either an acid or a base, depending on what it reacts with. By definition, at 25 degrees Celsius, we have another K, another equilibrium constant here, Kw. Kw is the water dissociation constant, okay? And it is always equal to this value, 1 times 10 to the minus 14th, at 25 degrees Celsius at least. Okay. What that means is in pure water, Kw is made from multiplying the H plus and the OH minus concentration from water. It always equals 1 times 10 to the minus 14th. And in pure water, both of these would be equal to 1 times 10 to the minus 7th. So it has some H plus, that's some OH minus, which is why it's amphoteric. It can act as an acid or a base. It has some H plus to react with bases. It has some OH minus to react with acids. It has both. And as we're going to learn, all things do, but in a different kind of way. No matter what the solution contains, the product of H plus and OH minus must always equal 1 times 10 to the minus 20 or minus 14th at 25 degrees Celsius. So there's 3 possible situations for solutions. And we're going to look at these 2 ions because H plus is kind of like the acid ion. OH minus is like the base ion. If you have an equal concentration of both, you have a neutral solution, which was the case with water we just talked about. It had the same amount of H plus and OH minus. And if it's pure water, it always will, which is why we consider it neutral. If you have a greater concentration of H plus ions, you are an acid. And if you have a greater concentration of OH minus, you are a base. Okay. We've talked a little bit about pH, I'm sure, in the other science classes as well. The formula for pH here is really important. We're going to use it in all of these different calculations. The pH is a logarithmic scale. It measures the concentration of hydrogen ions in a solution. If you take the negative logarithm of the H plus concentration, it gives you the pH. A lower pH actually means you have a stronger acid. The traditional scale goes from 0 to 14, but as we're going to learn and do examples, they can actually get below 0. You can have a negative pH as an extremely strong acid or a very concentrated acid. You can have ones that go way above 14 on the pH scale. The scale is just a logarithmic scale that basically tells you how strong something is or how acidic something is. A pH of 7 exactly is neutral. Anything greater than 7 is basic, and the higher the pH, the more basic. Anything lower than 7 is acidic. The lower the pH, the more acidic. There's a couple examples of some common household things. That would be slightly basic, slightly acidic, or very acidic, very basic. So you'll notice 1 molar NaOH and 1 molar HCl at the very top and bottom. at 0 and at 14 pH. And then just some common things kind of in between. Pure water being right in the middle, milk being very basic or very slightly acidic, blood being very slightly basic. Things that are like sour tasting, vinegar, lemon juice, stomach acid are all acidic. Household cleaners, detergents, soaps, and stuff like that will be on the basic side. Most foods that we eat are acidic. Okay? So lots of things that we eat have acids in them. We don't eat nearly as many bases. There's a few things, but not very many. Here's a couple of other times we use this sort of logarithmic scale. And I should mention, going back here real quick, a logarithmic scale means that if I compare the pH between 3 and 2, that actually is not a difference of like, this is 1 time stronger, or like a little bit stronger, 50% stronger. This is a logarithmic scale, meaning every time you go up one number or down one number, it's getting 10 times more acidic or 10 times more basic. Basically what that means, if I'm comparing vinegar, which is a 3, with stomach acid, which is a 2, stomach acid is 10 times more acidic than vinegar, which makes a lot of sense because we would eat vinegar and things, but I don't know if we would eat stomach acid. It's 10 times more acidic than vinegar. Same things up here. Ammonia, the household cleaner, has a pH of 12. Okay, that's pretty basic, but it's 2 steps below NaOH, a strong base. Ammonia is a weak base, NaOH is a strong base. That means it's actually 100 times more basic. Okay, it's going to produce 100 times more OH minus molecules in solution, ions in solution. Okay, here's the POH, is also another formula we're going to use all the time. This is just like pH, but it measures how basic something is. You just take the negative log of the OH minus concentration. And then pK, we're going to learn a lot about in the next unit, and you're going to love it. To calculate the pH of a strong acid solution is actually really easy. You just use the pH formula. By definition, a strong acid will react to completion, or almost entirely to completion, meaning 100% of your acid molecules will turn into the ions. So it's actually going to make the math really easy. If you know the concentration of your acid, the concentration of your H plus will just be the same. So let's look at an example. Okay, what is the pH of a 0.25 molar solution of hydrochloric acid? Hydrochloric acid is one of our strong acids on our list, HCl. Okay. It is a strong acid. That means when I put HCl and dissolve it in water, 100% of it is going to split apart into an H plus ion and a Cl minus ion. 100%, which is why I'm just drawing a right arrow. This is not an equilibrium. This reaction proceeds 100% to the right. Now you'll notice on the slide here, they also write it, you can choose to write HCl plus H2O to get this H3O plus and Cl minus. I wrote this one on the right, and that's how I would normally write it because that makes sense to me. Adding the H2O is how you get H3O plus, which is called the hydronium ion. But it's really just the same as H plus. So I just choose to write this simpler version. I think it makes more sense. So 100% of these are going to split. So I have a 0.25 molar solution of this. Since all of it is splitting apart into H and Cl, it means I also have 0.25 molar of this. And 0.25 molar of this. 100% of these split apart. Well, now if I want to calculate pH, it's actually really easy. pH is just the negative log of the H plus concentration. So the H plus concentration is right here, 0.25. So let's do the negative logarithm of 0.25. Oops. 0.25. And you'll get your pH. When I do it in my calculator, I get pH equals 0.602. pH is definitely not always a whole number. A lot of the times it will be a decimal, or it could be a negative number, or anything like that. Okay? So that is the pH of that hydrochloric acid solution. You just take the negative log of your H plus concentration. A weak acid is going to make it more complicated, because a weak acid does not react to completion. It will not react 100% like our strong acid did. you're going to like when you have a strong acid or a strong base in a problem. It's going to make your math way easier. Okay? Only a certain percentage of the acid molecules break down into protons. Therefore, we need a way to know what percentage of an acid molecules dissociate. That's where the acid dissociation constant, Ka, comes into play. Ka is going to tell you the relative strength of your acid by telling you what percentage of it dissociates. Only weak acids truly have a Ka. Strong acids are by definition assumed to fully dissociate, which means they would have all products, zero reactants. Ka, just like K for equilibrium, is products over reactants. So in an example like the one we just did, right? If I have 100% products and no reactants, products over reactants would be some number over 0. Can't divide by 0. Okay? Because of that, strong acids don't actually have a Ka. So if I give you a problem, I give you the Ka of an acid, that means you know it's a weak acid. Okay. Calculate the pH of a weak acid. I give you a little set of instructions on there for how to do it. It's a little bit complicated. This is where the equilibrium stuff is going to come into play. You're going to write the balanced reaction of the weak acid dissociating. Remember that it's in equilibrium, so write the double arrow for this one. You're going to write an ICE table and fill in any information about initial concentrations given to you in the problem. You're going to write the equilibrium expression for Ka, which is identical to writing Kc or Kp, it's just products over reactants. You're going to determine the direction the reaction will proceed by either solving Q, which we don't really ever have to do, or knowing the reaction will proceed towards the side with 0 initial concentration, just like we did with EQ. If there's 0 of a product or a reactant, then you know it's going to go that way because there's none of that side to start the reaction the other way. You're going to subtract X from the sides where the concentration is decreasing, add X to the other side, substitute the equilibrium concentrations into the equilibrium expression, Ka, and solve for the equilibrium concentration of H+. That's all exactly like last unit. You set up the ICE table, do the exact same math. The only thing that's a little bit different is now we can solve for pH afterwards. We're going to find the H+ concentration, use that to solve for pH. Basically, again, the process of finding pH for a weak acid or base is nearly exactly like an equilibrium problem. Using an ICE table will help you keep your work organized, and I would highly recommend it. So let's look at an example of a weak acid. So we're going to say bye to this really nice, easy to find pH, and we're going to do this problem instead. Okay, so I have this time, just like last time, I have a 0.2 molar of an acid. Except I have acetic acid, which is one of the weak acids I told you. Okay, even if you didn't know this was a weak acid, the problem gives you a Ka of this acid, so you know it has to be a weak acid. The Ka of acetic acid is 1.8 times 10 to the minus 5. This is not something you need to know. This will be provided for you in the problem. Okay, so I know this is a weak acid, which means it's going to break down, but not 100%. It's going to be in equilibrium. So what I would do is write my reaction, draw my equilibrium arrow, and this is going to split apart just like our other acid did. I'm going to make an H plus C2H3O2 minus acetate. But I'd make sure to draw my equilibrium because this is not going to go 100%. When I deal with equilibrium, I draw an ICE table to help. I'm going to put my numbers into the ICE table, 0.25, 0, 0. Okay. Always, like most of these problems, we're going to have 0 things over here to start with because we're just seeing how this dissociates. So we're going to go to a time initially before it gets put into water. If I change, my reaction has to go to the right because I have 0 and 0 over here. So I have minus X plus X plus X, just like equilibrium. 0.25 minus X, X, X. Right, my change is my C, so I have 0.25 minus X equals 0.25 minus X. We don't know what X is exactly yet. We'll solve for that in a bit. I'll just drop down the X here and here. Now, once we have our equilibrium concentrations, we're going to write our Ka. We know the value of Ka is 1.8 times 10 to the minus 5. We know it's going to be equal to products over reactants. First product, H+. Second product, acetate. My reactants, acetic acid, HC2H3O2. Okay, so now I'm going to plug in my equilibrium concentrations here. Remember, never plug in these, right? Because you can't solve for K unless you're at equilibrium. So I'm going to plug in my values, 1.8 times 10 to the minus 5 equals, this is X over 0.25 minus X. Okay. Now, we could solve and simplify all of this, solve the quadratic formula to find X exactly, or we can take the same approximation we did last time. If you notice, K is a really small number. And a little hint, with all weak acids and weak bases, Ka will always be a really small number. Well, not always, almost always. Majority of the time. So what that means is X is going to be a really small number. Only a little bit of this is going to go to the right. So this minus X or this plus X is going to be a really small number because this is mostly reactants. This isn't going very far to the right at all. So what that means is I can do 0.25 minus X and just get rid of that minus X. 0.25 minus a really, really small number is basically just 0.25. Now solving for X will be much simpler. 0.8 times 10 to the minus 5 equals X squared over 0.25. And now I'm just going to solve for X. Multiply 0.25 up here, and then take the square root of it. I get X is equal to 0.00212. Okay, but what does X tell me? I have to go back to my equilibrium to figure that out. It could tell me my new concentration of acetic acid. I can do 0.25 minus this number. See, this number is really, really small. So 0.25 minus 0.00212 is basically just 0.25. But it also tells me X and X. Well, if I go back to the problem, I wanted to find pH. Remember, pH is just the negative log of the H plus concentration. So if I can find the H plus concentration, I can find pH. X is 0.0212. H plus is just X. Okay? So that's what we found. So I'm just going to plug that number into the pH formula. Solve for pH. I get like 2.67 rounded. So this acetic acid is definitely an acid. It has a low pH, but not nearly as low as our strong acid of the same concentration. Okay, so that's how you calculate the pH of a weak acid. We're going to do a similar thing later for a weak base. This is probably the most important math concept from this chapter. We're going to do this a whole bunch, and in the next couple of units as well. All right, so just one more thing we're going to kind of add to that problem is called percent dissociation. This is basically just a measurement, a percentage measurement, of what percentage of your solution turned into H+. Okay? So percent dissociation is equal to the amount dissociated, which is what we just calculated for X. That's how much H+ was made, divided by our initial concentration of acid, times 100%. Okay, so just real quick, if you didn't get that formula all the way, that's fine. Just hang on a second. I like to do just like percent dis. Dissociation is a long word, and I'll know what you mean. It equals the amount dissociated. That's how you spell amount. Let's just pretend. Amount of H plus divided by the initial concentration of acid. Okay. So my amount of H plus I found is X. My H plus concentration at equilibrium was 0.00212. My initial acid concentration is 0.25 molar. multiply by 100, and that's your answer. That'll tell you what percentage of your acid turned into H plus ions. It's usually going to be a really small number for weak acids. So only 0.85% of my initial acetic acid turned into H plus. That's why my Ka is so small. Yeah, I just did that. Sorry. Okay. 4.6 is on 14.6 is on bases. So a couple definitions, like we said, Arrhenius bases produce hydroxide ions, OH minus ions. Bronsted-Lowry definition says that bases are protons acceptors. So there's two ways to think of bases, and sometimes we'll have to use either one, depending on what the base is. So a base is something that gains an H plus, or a base is something that when you dissolve it in water produces OH minus. In reality, that means the same thing, but it might be harder to understand when something's a base. Strong bases, just like strong acids, can be considered to dissociate 100% in aqueous solutions, or another way to say that would be to accept protons 100% of the time in solutions. Ionic compounds containing OH minus are generally considered strong bases. So all the group 1 elements, when combined with hydroxide, are strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, and most of the group 2 elements. So these 3 group 2 elements are also strong bases with hydroxide: calcium hydroxide, barium hydroxide, and strontium hydroxide. All of these, when you dissolve them in water, will fully split apart into their cations and anions, into like lithium and hydroxide, for example. Remember that weak acids have a Ka called the acid dissociation constant. Bases have one as well. Weak bases have a Kb called the base dissociation constant. It's exactly like Ka, but instead it just tells you how a base reacts. Okay, so here this reaction is a base plus a proton, because remember they're proton acceptors, they're going to gain protons, gives you BH plus, which would be a weak base. You can write Kb from this general reaction, products over reactants. Kb works exactly like Ka. Ka and Kb are related to each other as well. If you have a pair of conjugate acids and bases, their Ka times Kb always equals this number. If this number looks familiar, that was the number for pure water. If you multiply the acid dissociation constant of an acid of a conjugate acid-base pair times the Kb of the conjugate base of the conjugate acid-base pair, numbers will equal 1 times 10 to the 14th. What that means is if you know the Ka of an acid, you know the Kb of the conjugate base, or vice versa. If you know the Kb of a base, you can find the Ka of a conjugate acid. Because that's a lot of science words, let's do an example of that real quick, just to see if you know what I mean. Okay. So here I have I'm going to find the Ka of NH4 plus, Ka of the ammonium ion. The Kb of NH3 is 4.8 times 10 to the minus 5. Okay. So first thing you might not know, these are a little bit harder to understand what's an acid and what's a base. Okay. Remember that, okay, this one, the easiest way is just like this one has a Kb. NH3 is ammonia. It has a Kb, so this is a base. Okay. NH4 has a Ka, so it's an acid. Also, we could think about how these two things are related by their reaction. So I could think about it either way, NH3 and NH4 plus. These things are related, they're only different by 1 H plus. So if you take NH3 plus a hydrogen ion, you get NH4 plus. So this is a conjugate and acid-base pair. They're separated by only an H plus. What that means is the Ka of NH4 times the Kb of NH3 equals that magic number, 1 times 10 to the minus 14th power. So I know the Kb of NH3 is 4.8 times 10 to the minus 5. I'm just going to plug that in. equals 1 times 10 to the minus 14th still. And now I just solve for Ka. Divide by this to get Ka is equal to 2.08 times 10 to the minus 10. Okay. Sometimes we'll have to do this. When we get to the last type of problem on our PowerPoint today, we'll have to do this sort of relationship. And we'll talk a lot more about it in class as well if it's a little confusing. Okay. More importantly, though, we have calculating the pH of a strong base. You're going to find the OH minus concentration, very similar to how we found it for an acid. Okay. Well, when it gives up an OH minus in solution, so we can't directly find the pH, but what we can do is find the pOH. Remember, pOH is the negative log of the OH minus concentration. It's a scale that measures how basic things are. And then pH and pOH are related by this formula. pH equals 14 minus pOH. Or, another way to write that, pH plus pOH equals 14. Just rearranging it. That's how I usually like to write it. I like how that looks. Okay. pH plus pOH equals 14. So if something has a pOH of 4, you could solve for its pH, right? Just pH would be 10. pH and pOH are going to be basically kind of like inverses of each other, but they're inverted at the number 7. Okay. So like this one is 3 below 7, this one's 3 above 7. Let's look at this example. I want to find the pH of this barium hydroxide solution. Okay. Barium hydroxide is one of the strong bases, which is great. We're going to draw a regular facing arrow because this is going to 100% split apart. This is going to split apart into barium 2 plus and OH minus. But I also need to make sure my reaction is balanced. I have 2 OH minuses here, so I need to have 2 OH minuses here. So this one actually splits into 2 OH minuses. Well, that's fine. I have a 0.10 molar barium hydroxide solution. And this is going to fully split apart. So this is going to split into 0.1 molar barium. And it would be 0.1 molar hydroxide, but my stoichiometry here says that I make 2 for every reaction. So it's actually going to be 0.20 molar hydroxides. This 1 molar or 0.1 molar barium hydroxide splits into 0.2 molar hydroxides because it makes 2 every time it splits apart. So I want to find the pH of this to answer my question, but there's no H plus in this reaction, so I can't find this yet, but I can find pOH because pOH is the negative log of the hydroxide concentration, and that is what we have right here. So for pOH, I'm going to plug in negative log of 0.20. Plug that into my calculator. If logs freak you out, you just have to plug it into your calculator. You don't have to do it in your head or anything like that. I get 0.699 is my pOH. Now I can find the pH because pH plus pOH equals 14. pH plus 0.699 equals 14. So pH must equal, what's that, 13.3, something like that. Calculating the pH of a strong acid or strong base is much easier than the weak varieties. So let's get right into the weak variety then. What's the pH of this 0.1 molar NH3? Now, NH3 doesn't have an OH in it. It's not required to have an OH in it, but let's look at this reaction that's given to you in the problem. NH3 turns into NH4+. Okay, so what's happening to NH here is it's gaining another H+. It's going from 3 to 4 hydrogens, and it's getting a plus charge. This is an example of a base that uses that second definition of a base. It is a proton acceptor or it's a hydroxide donator. Those are kind of the same thing because this also makes a hydroxide, but it might be confusing where that comes from. Another identical way to write this reaction real quick is if you take NH3 plus water. When NH3 reacts with water, water itself can be kind of split apart into H plus and OH minus, like we said. So this NH3 is a proton donator. Sorry, it is a base, so it is a proton acceptor. I see a proton here, so it's going to take that to make NH4 plus, my conjugate acid. Well, now I have this OH minus left over, so that's what I have here. So this is the actual full reaction here, right? And this actually makes sense. It's all balanced and stuff like that. But sometimes you write a little shortcut, and you'll see both. So I wanted to show you both. Okay? The reaction here is the same. It just also has this water. Well, when we do any of our math, water is a liquid. It does not get included in the equilibrium expressions. It does not get included in the ice tables. It doesn't really matter. So feel free when you have something like ammonia to write this out with water or without water. In the example I have here on your paper, it doesn't have it written in there because it's not going to end up mattering. I have NH3 in equilibrium with NH4 plus and OH minus. I'm going to set up our ice table. My initial concentration of NH3 is 0.1 molar, and I have none of this to start. The last bit of info, it gives me the Kb of NH3. This is going to let me set up an equilibrium expression for NH3. All right, eventually I want to find its pH. Let's do it. My change, my reaction has to go to the right because there's 0 of this and 0 of this. Minus x plus x plus x. 0.10 minus x, x, x. Those are my equilibrium concentrations. Let's solve for x. So I know my Kb, 1.8 times 10 to the minus 5 equals products over reactants. So it's going to be x times x. Remember, these only have a coefficient of 1, so I don't have to square them or anything like that, which would be a case for any monoprotic acid or base. Okay. And 0.1 minus x will go down here. Now I can solve this fully using the quadratic formula, or we can make that approximation. Kb is a very small number here, 1.8 times 10 to the minus 5. That is small enough to let us get rid of this minus x to make our math easier. All right, let's solve for x. 1.8 times 10 to the minus 5 equals x squared over 0.1. Multiply my 0.1 up here and take the square root. I get 0.00134 equals x. Just like in the last problem, x tells me information if I go to my equilibrium row. X, what really matters here, gives me my OH minus concentration. So this is also equal to the concentration of OH minus. I want to find pH. This doesn't help me directly, but I can do what we did in the last problem. Find the POH and then just turn that into pH. POH is the negative logarithm of the hydroxide concentration, which is just this number. So our POH when we solve this is equal to 2.873. To find pH, it's just pH plus POH equals 14. The POH is 2.873 equals 14. pH just equals just like 11.127. That's the pH of my solution. Using ice tables, writing out the formulas exactly like we did in the last unit. If you can do these skills, you will succeed on this unit. If you can't, you're going to have a really hard time. Okay, just a couple more things to go. We're almost done with it for today. Polyprotic acids are acids that can dissociate more than one proton. So it's like the diprotic or the triprotic acids, H2SO4, H3OP4. These dissociate in a stepwise manner, one proton at a time, and each step is going to have a different Ka associated with it. So let's break down step 1 here. I have H2CO3, carbonic acid. It splits apart. It's going to lose one H plus and turn into its conjugate base, HCO3 minus. This has a Ka of 4.3 times 10 to the minus 7. So it's actually a pretty weak acid. Well, I still have an H available, so the second step can occur. Once I have HCO3 left over, this can break down into an H plus and the carbonate ion. This Ka is even smaller than the first one. The conjugate base of the first association equilibrium becomes the acid in the second step, and it can keep going until you run out of H's, but it'll usually only be like 2 or 3. Okay. Well, this looks like it'd be really annoying, and it can be, depending on if you want to calculate it all, but there's actually a shortcut we can use that makes it much simpler. As the negative charge of the acid increases, it becomes harder and harder to remove successive protons. So comparing these two back in this problem, step 1, a lot more protons fell off. That's why Ka was a bigger number. Still a small number, but much bigger than Ka2. And each step, this number is going to get significantly smaller. It's going to get so small to the fact that 99.9% of my H plus ions in my solution just came from the first step. Every other thing after that is just like scraping the bottom of the barrel for just a couple of more H pluses. And my next step would be just a couple of more H pluses. For a typical weak polyprotic acid, Ka1 is significantly stronger than Ka2, which is significantly stronger than Ka3. Because of that, only the first dissociation step matters for pH. 99.9% of the hydrogen pluses are just going to come from the first step. So here we have an example of what a problem can look like. This problem would be the problem from hell if we had to do it fully all the way out. But we're not going to have to. Calculate the pH of a 5 molar solution of phosphoric acid, H3PO4, and the equilibrium concentrations of the species H3PO4 and H2PO4. Notice I have 3 Kas here. This has 3 protons. The first proton that falls off has this Ka. We'll be left with H2PO4. Its Ka would be much smaller. All right? It would make HPO4 2 minus. And then HPO4 2 minus would lose its other H, but that's really, really unlikely to happen. Okay? So what we have to do when we're given a problem like this is just worry about this one reaction. We don't have to do all 3 of the different steps. If you would like to work out all 3 of these dissociations, you'll need 3 separate ice tables. You'll need to solve for Ka every time, find your concentration of H. You could work it all the way out and get the exact number. And if you want to, go for it. But we like making approximations to make our work much easier. All right, so let me actually copy this down just for a second. I have my ice table, my H3PO4, equilibrium with its first H plus and H2PO4 minus. You might be a little curious about this, just kind of coming to mind. The base we had fully split apart into its OH minuses in one step. And that's how it'll work. Bases don't care, especially the strong base. It really will just split apart into everything in one step. Technically you don't need a Kb for this at all because it's strong. But like if this was a weak base, the same thing would apply. Acids are just kind of special. All right, so here's my reaction, my ice table. Okay, I'm going to plug in my initial concentration. I have a 5 molar solution, so 5 molar will go there. As always, I'm going to assume I have none of this to start with. Just you wait, though. Eventually we'll get there, where we have to start with stuff on that side. Ka1 is the one I care about here, because that's my first dissociation, is kind of a reasonably large number. This isn't super big, obviously, but it's actually going to be too big to do the approximation with. And I'll kind of show you why as we go. Okay, that should be everything I need. Again, I want to find pH, and I want to find the concentration of this at equilibrium. Minus x, all 5 minus x, plus x. I have x plus x. I have x. Ka equals 7.5 times 10 to the minus third. That'll be x times x over 5 minus x. So this number is not quite small enough to not matter. By the time we take the square root of this, it's actually going to be a pretty reasonable number. So it's going to be like 0.2 or something. Your rule of thumb that you can use. What I'll tell you, if you have a number times 10 to the minus fifth or smaller, so it could be minus fifth through minus 14 or even higher, it's super safe to use the approximation. Anything 10 minus 4 all the way up to like 0, if you're in this range of exponents, it's not safe. 4 is kind of the cutoff. You can get away with doing it with minus 4, but anything less than minus 4, or I guess greater than minus 4, would be a no-go for using the shortcut method. So this one we're going to work out all the way. Well, to save your time, I'm just going to give you the answer, but in class we would work this out all the way. Can't get rid of this minus x. So we're just going to multiply it up here. Multiply this entire quantity, 5 minus x equals x squared. I'm going to need to distribute this 7.5 times 10 to the minus third to both these numbers. If that freaks you out, just know this is the same thing as just 0.0075. You could write that instead. Distribute it. I get 0.0375 minus 0.0075x equals x squared. Now to solve for x, I'm going to get everything on one side, so I'm just going to add everything over to this side. Okay, x squared plus 0.0075x minus 0.0375 equals 0. I'm going to magically do the quadratic formula in just 1 second and get my x is, I get two values, one's positive and one's negative. Can't be the negative one because then I would have a negative concentration of these things, which is impossible. So I know x is this number. X is a pretty large number here, actually. So like if I did 5 minus x, that would be a pretty significant change. The threshold is usually like a 5% change is too much, but this is fine. X is 0.1899, so that's my H plus concentration. It's also my concentration of H2PO4 minus, which is one of the things I was trying to find. So I found that part of my answer. Now I just need the pH, which is just going to be the negative log of my H plus. pH equals 0.721. You gotta love this part of chemistry where every problem takes a full page to solve. All right, so last thing we have to talk about today is salts. Salts dissociate into their ions when they dissolve in water, meaning they're split apart into the positive and negative parts. We usually think of salts as being neutral. They don't react with stuff. They're just kind of there. In an acid-base neutralization reaction, we made NaCl salts and like, yay, we neutralized our salt. But actually some salts are acidic or basic. It depends on what they're made of. A salt like NaCl is a neutral salt because it doesn't affect the pH of water when you add it. No matter how much salt you add to water, it won't change its pH. But what about NaCl makes it neutral? Why is that the case? Why are some acidic, some basic, some neutral? Let's start with what makes NaCl neutral. It's the ions it's made of. NaCl will split into Na plus and Cl minus. Okay, these ions are kind of special. They are the conjugates of strong acids and bases. Okay, so let's one at a time. Cl minus is one of the things it makes. That is the conjugate base of hydrochloric acid. HCl is a strong acid. It makes Cl minus. Na plus is the cation or the conjugate acid of the strong base sodium hydroxide. They're only off by one OH. Okay. The conjugates of strong acids or bases do not react with water, therefore do not produce any acids or bases in solution. Okay. So anytime you have something that comes from a strong acid, or is one of the components of a strong acid. Got to remember that list of strong acids. So anything with like for sodium or lithium or potassium, those things make strong bases. Or things like bromine and nitrate and phosphate and things like, not phosphate, sulfate make strong acids. So those things don't affect the pH of water. Let's compare it to what we're going to do with acidic salts. These two are examples of acidic salts. We're going to talk about why. NH4Cl, ammonium chloride, and aluminum bromide are examples of acidic salts. And we're going to break down why. Let's just do one of these examples. AlBr3 breaks down into the two components, aluminum 3 plus cation, Br minus anion. Br minus is the conjugate base of the strong acid HBr. So it doesn't react with water at all. So I basically just ignore it. This Br minus does not affect our pH. But Al3 plus is the conjugate acid of a weak base. There's no strong base with Al to start it. Therefore, when I put this in water, it will react with water to produce a weak base, AlOH3, and H+. Because this produces H+ when it's put in water is why it's acidic. We can calculate the pH of the solution by calculating the H+ concentration. Thinking a little bit more about it, we have our two components. We have bromine. Our Br minus, when we add it to H2O, has no reaction. And let's think about why that is. Br minus has no reaction here because let's flip this reaction around. When we started with HBr, our strong acid, we said we draw a regular right-facing arrow because 100% of this turns into its two components, H and Br minus. This reaction proceeds entirely to the right because HBr is a strong acid. So it doesn't go any bit to the left at all. And this version up here is the flipped reaction. So this reaction doesn't work because it's 100% the other way. But if we look at the other component of that salt, the aluminum, that does combine with water. And notice this time we have our equilibrium arrows. The aluminum and hydroxide are going to, or the water are going to come together to make aluminum hydroxide and H+. The positive charge here is going to attract the OH from water, and you'll be left with just one H+ as your other product. Since AlOH3 is a weak base, this reaction occurs at an equilibrium. Calculating the pH of this works just like a normal acid-base problem. There's a lot of information there, okay? Basic salts are salts made from the cations of a strong base and the anion of a weak acid. Examples include NaF, sodium fluoride, calcium fluoride, and NaCO here, sodium acetate. These will produce a weak acid and hydroxide ions in solution. Keep in mind the Na plus and Ca2 won't react with water because they come from the strong bases, sodium hydroxide and calcium hydroxide. Let's look at some bases, break it down, and try to figure out which of these are acidic, which of these are basic, or which are neutral. So let's start with NaCl. Okay, it helps to think about these as two individual components, Na plus and Cl minus. Okay, we're going to add these to water and see which ones of them actually make strong acids and which ones don't. Now, easier way to think about water is by splitting it apart into H plus and OH minus. Okay, so Na plus is going to react with OH minus to make NaOH, which is a strong base. H plus will react with Cl minus. I know these are the things reacting because I'm looking at their charges. The positive and negative attract and those react. Positive and negative attract and those react. H plus, Cl minus make hydrochloric acid, which is a strong acid. Okay. Because of that, neither of these are weak. So neither of these are actually going to react with water. This is a neutral salt because I have a strong acid and a strong base. For the next one, let's look at BaF. Made of the components barium 2+, fluorine 1-. This is going to join with OH minus. This will join with H plus. This will make barium hydroxide. This makes hydrofluoric acid. This is a strong base. It's on the list. Highly recommend memorizing those strong bases I gave you. This is a weak acid. Okay. Fluorine anion makes a weak acid. So that means we have some work to do with fluorine. Strong base we can't do anything with. It doesn't react with water. But we can take this F minus, add it to water. This reaction will occur because it is in equilibrium because it's a weak acid. So I'm going to take my original anion, add it to water. This is going to make HF like we said. Okay. That takes the H plus away from the water. And we're left with the OH minus part of the water. This is the reaction that occurs when F minus anion mixes with water. It makes some hydrofluoric acid, which is a weak acid, but the key here is that it makes hydroxide. Hydroxide is what makes something basic. Because this anion produces hydroxide, this is a basic salt. If you take this salt and put it in water and measure its pH, the pH is going to go up, making it more basic. All right. Next example here, NH4Br. Okay, we're going to see how this reacts with water. This is made of ammonium and bromine. NH4 plus will react with the OH part of water. We've talked about NH4 a little bit. It's easier to usually think about this reacting as a proton donator. It's going to make NH3 basically, plus H2O. So that's kind of how this ends up reacting. And Br minus will react with the H plus to make HBr. Don't worry so much if this is confusing. NH3, though, is not on our list of strong acids. It is, or strong bases. It's not on either list, I guess. But it is a weak base. So we have some work to do with ammonia. This is a strong acid, though, which disqualifies this one. Br minus will not react with water because it makes a strong acid. It means the conjugate base is extremely weak. It cannot react with water. All right, so our reaction here with NH4 plus and water. We want to see what happens when these two things join together. All right, so kind of like before, this is the positive, so it's going to attract the negative part. It's going to attract the OH minus. Okay, the OH minus is actually going to take the H plus away to make more water. So the water ends up just kind of going away here. When you add OH minus to this, it makes NH4 plus OH minus. So it actually ends up turning into NH3 plus water, and the water just kind of goes away into the solution. It's really weird looking. That's why it's sometimes helpful to think of NH4 plus as just donating a proton. It donates a proton away and just ends up as NH3. Well, the other part of this water that was not donated is the H plus. That's our second product. NH4 plus water yields NH3 plus and H plus. The water kind of goes away. Okay, that's a lot. Go through all of that more to get that idea in our heads. But H plus is produced here. H plus makes things acidic. So this is an acidic salt. Okay. Instead of going through all of this thought process, super convenient shortcut you can use. Once you're figuring out if something is a weak acid or weak base, strong base, let's look at what we have here. BAF is made of a strong base and a weak acid. Strong base combined with weak acid makes a basic salt, which kind of makes sense because the strong base is more powerful than the weak acid. So we're left over with a little bit of base. Down here, I had a strong acid, a weak base. The strong acid is stronger than the weak base, kind of overpowers it. The salt is acidic. Let's just apply that real quick to our last one. NaF. Na makes NaOH. F makes HF. This is a strong base. This is a weak acid. Strong base is going to overpower the weak acid. This can be a basic salt. If that makes more sense, 100% go for it. Not gonna lie, I hate salts. So, all right, we have these two examples to do real quick. Let's, to save time, we're already running a little late here. We're gonna skip this first one. We'll talk about it in class. Let's do the second one here. I'm gonna calculate the pH of 0.1 molar NH4Cl solution. I have its Kb of NH3 equals 1.8 times 10 to the minus 5. Now, I need to read this very carefully. This is the Kb of NH3, which is over here on this reaction, which is kind of weird. We're dealing with NH4, but it gives us NH3's Kb, so we'll come back to that in a bit. My reaction's already written for me nicely. NH4 plus H2O yields H plus NH3. Draw my ice table here. My initial concentration of this is 0.1. Then it comes to water. Water is a liquid. I don't care about it. I'm just going to exit out. Anywhere you see water in this or any other solid or liquid, just cross it off. Just ignore it. It's not included in Kb or Ka. 0 of this, 0 of this. Minus x to get 0.1 minus x. Plus x, get x, plus x, you get x. Okay. Now, if I solve for x, I'm going to be able to get my answer. I'm trying to find pH again. There's one extra trick thrown into this problem. Okay. This is what's dissociating is NH4 plus. But it gave me the Kb of NH3, which is over here. I can't do the dissociation of NH4 from NH3's number. NH3 is not what's dissociating here. I need to know NH4 plus. What I need to know about it. Okay. Let's look at what's happening to NH4 plus. It is going this way. It's going to be losing an H plus and creating a base. So going this direction, NH4 is actually an acid, but it gave you a Kb for this, which is a base. Okay. NH4 plus and NH3 are conjugate acid-base pairs. If I multiply Ka times Kb, it equals the magic number, 1 times 10 to the negative 14th. I have the Kb of NH3. Okay. I'm going to plug that into this formula. And I can use that to find Ka. I'm going to solve that. The Ka of ammonium ion is 5.56 times 10 to the negative 10th power. I think we already did that problem earlier today, so we got the same answer here. This is what I need because I want to learn about my thing on the left here. That's what I'm starting with. This is what is dissociating. So I need its information, not NH3's information. That doesn't help. But I use this NH3's information to help me figure out this one. So my Ka is my products over reactants, H plus, NH3 over NH4 plus. My Ka I found here. X over 0.1 minus x. This number is plenty small enough to make this approximation. So I get that out of here. Equals x squared over 0.10. Multiply 0.10, take the square root. X is going to be a pretty small number this time. 7.45 times 10 to the minus 6. That is x, which also tells us H plus concentration. I want to find the pH of this, so I take the pH of the H plus concentration. 7.54 times 10 to the minus 6th. And I find the pH of that, that equals 5.13. This is a slightly acidic salt. Okay. 5.13 is its pH. All right, so just to summarize here at the end, very difficult chapter with all the math and stuff like that. I'm going to give you some information, some flow charts to help you with some problems. We're going to do lots of practice of these different types. If the last one tripped you up a bit, that's totally acceptable. It tripped me up a bit too, trying to learn how to teach that to you. The most important first step is identifying what sort of solution you're dealing with. Is it an acid? Is it a base? Is it strong? Is it weak? What am I calculating? If it's a salt, is it reactive? Is it an acid? Is it a base? Like, what am I doing? I think the math is easy. It's just like getting started. So for strong acids and bases, it's easier. Look for major species in the solution. Look for reactions that can be assumed to go to completion. Strong acids, strong bases. Concentration of products will equal the initial concentration of acids or bases. We just use that to find pH or pOH. This is just like what we've done in honors chem before. For weak acids and bases, we have all of these sort of steps here. Okay. I'm not going to read through all this again because we already kind of summarized it in our instructions. But yeah, that's acids and bases, unit 14. This is our introduction. Doesn't mean it's easy. It's a pain in the butt, okay? So a lot of these math problems, we're going to finish up that last one I left blank. We'll do that one in class. It's good practice. And we're going to do our unit 14 worksheet and get all caught up with it. Okay. Hopefully that made sense. Hope you have a good day.